Have you ever wondered why you see less animals out and about in the wintertime when the weather gets colder? Well, it could be because the animals that you're looking for are in a state of dormancy. Wintertime can be tough to survive. Biological and chemical processes can be hindered, food availability may become scarce, and extreme weather can pose hazardous threats. Animals that live in environments that experience extremely cold winters or constant cold temperatures must be able to adapt to the hardships that come along with it. Animals prefer to be in a zone of normothermia, which is a thermoneutral zone. So that means it's not too hot, it's not too cold, but it's just right. The zone of thermogenesis is below the lower critical temperature. It is here where the metabolic rate increases as the outside temperature decreases. Essentially, an animal has to raise their metabolic rate in order to raise their body heat in order to survive the colder temperatures. If an animal has already maximized their metabolic heat production and the temperature continues to drop below the lower lethal temperature, then the body temperature will start to decrease.
This right here is where an animal will be in normothermia. It's where it wants to be. Now, when it gets to a lower critical temperature, that's when it starts to raise its metabolic rate, and that thus raises its body temperature. Now, if it goes lower than the lower critical temperature and gets into the lower lethal temperature, that's when hypothermia is at risk for this animal.
Since the rates of chemical reactions that produce metabolic heat are sensitive to temperature, a positive feedback loop will be triggered, eventually leading to hypothermia, which will then lead to death. Animals in environments lower than the lower critical temperature can show several different adaptations to handle this cold, like having fur for insulation. Thick fur is energetically costly to produce, however, and this might not be suitable for all animals in every climate. Cold winters with low food availability has led to a bottleneck effect on where animals can survive, and thus has led to the evolution of dormancy, evolving in several different types of species. Dormancy is a reversible seasonal phenotype in which an animal greatly reduces its metabolic rate and goes into a controlled state of being greatly inactive. They will also exhibit a low body temperature. Several different types of dormancy vary in their length and degree. Torpor is a type of dormancy that is frequently used in smaller mammals and birds. I mentioned earlier, when the temperature begins to drop below the lower lethal temperature, the animal's metabolic heat production will increase, thus warming the animal. However, this is very energetically costly to the animal. You have to make sure you have enough calories in your body in the first place in order to generate this heat from the metabolic increase, which is usually pretty hard in the winter, considering that wintertime comes with food scarcity. So in order to combat this problem, animals go into torpor. When an animal goes into torpor, the animal will experience many physiological changes. Their metabolic rate actually decreases, and their body temperature also decreases. Torpor is great for diurnally active endotherms, like squirrels and chipmunks, when faced with a long, cold night. When in torpor, the body temperature of an animal can reach just 1 degree Celsius above the ambient temperature, and in some species of bats, they can even reach a temperature that's just above the freezing point of their tissue. Oxidative metabolism is reduced to as little as 1/20th of their regular rate when they're not in torpor. This means that they need less food, less calories in order to survive, because they're burning less and they're still surviving the cold weather. Respiration also greatly decreases. Blood flow to the peripheral tissues is almost completely ceased. This is so that the internal organs get priority with blood flow. Voluntary motor responses are almost completely reduced, but some animals can still maintain some sensory perception, but it's usually just a little tiny amount of it. This type of dormancy is great if you need to survive a random cold night, but it definitely doesn't come without any negative sides. As you can imagine, getting yourself out of this type of dormancy takes a lot of energy, just like when you're in a really deep sleep and that alarm clock doesn't quite do the trick to get you out of bed. When an animal is ready to arouse itself out of dormancy, it has to burn its brown fat, which is a type of metabolic tissue specially designed for heat production. They have to increase their metabolism greatly in order to even begin their arousal, which is absolutely very energetically costly. Doing so takes more energy than just regularly existing.
When an animal is torpid, it saves energy by having a lower metabolic rate. When the animal is ready to arouse itself and come out of torpor, it has to spend energy over here by having a higher metabolic rate. Overall, you can still see that the energy spent is far less than the energy saved.
The reason we generally see torpor being used by smaller mammals and small birds is because it takes more energy for larger animals to get themselves out of torpor, and for smaller animals, it takes more energy to maintain a higher body heat when it's cold outside. Because of the surface area to volume ratio, larger animals have a harder time coming out of torpor. It takes them more energy to do this. This is because they have more tissues to rewarm. As I mentioned earlier, hibernation can vary in lengths and degree. Longer types of dormancy can last for an entire season, like hibernation, what we always think about with bears sleeping in a cave. Like other types of dormancy, hibernation follows the same trends of what happens within the animal's body and the reasoning for this to happen. If an animal is in hibernation, their metabolic rate will decrease, and this will lead to a lower need for food and water consumption. The benefits of hibernation are pretty obvious. I mean, it's kind of like when I go down to my refrigerator, see there isn't really anything interesting to make for dinner, and I just decide to go to bed because, I mean, you can't be hungry if you're asleep. Other than the obvious benefits like not having to freeze to death and not starving to death, hibernation comes with some interesting reasons why mortality rates are lower. Studies have shown that for small animals that hibernate, the mortality risk is 5 times less during the hibernation season than the active season. Why is this? Well, for one, we have to keep in mind that hibernation involves going into a completely comatose state, where movement is almost completely non-existent. Non-hibernating rodents have to maintain a minimum level of foraging activity in order to avoid starvation, which makes them more susceptible to predation. Because of the hibernating animal's lack of activity, coupled with the fact that they usually do so in a discrete location, the risk of predation is greatly reduced for them. Other problems such as infection or random accidents are way less likely to happen as well. Interestingly, studies have shown that hibernating animals have a higher annual survival rate than their non-hibernating counterparts. For example, dwarf lemurs can be found in tropical dry deciduous forests as well as rainforests. The populations that live in the dry deciduous forests have to hibernate in order to avoid the less than favorable conditions, whereas their rainforest counterparts have no hardships to face that would bring them into a state of needing to go into hibernation. The lemurs that take part in hibernation have higher annual survival rates than the ones that do not take part in hibernation. So clearly, besides just having to find some way to survive, hibernation can bring forth many benefits, like living longer. We're familiar with the life history theory, where longer-lived animals tend to live longer than shorter-lived animals. Some people think that hibernation may have something to do with an animal's ability to live longer. We don't really see those short-lived species taking part in hibernation. Since hibernating species don't have to scrape their teeth to get by during the winter, they can spend more energy in the productive seasons and use those reserves for things like mating. Like everything in nature, there's always a cost and a benefit to almost anything. Although hibernation does generally lead to lower rates of predation, if a predator does happen to stumble across a hibernating animal, then they pretty much don't have any defenses to protect themselves. Since sensory information is almost completely reduced, they might not be able to even detect that a predator is approaching them. Another interesting potential benefit to hibernation is an animal's ability to geographically expand. If an animal has evolved the ability to tolerate cold winters and colder conditions in general, then this means that they can expand their geographical location to places where other animals perhaps couldn't. They can then fill different ecological niches, potentially leading to more success in their species. But what about aquatic animals? What happens when the water that they're in freezes? I wonder if they're capable of dormancy, or what type of strategies they're capable of to tolerate the cold. When ice thickens over a lake, it essentially is like a lid on top of the ecosystem, trapping everything underneath. This layer of ice severely cuts down on the light availability, cuts off almost all gas exchange, changes the phytoplankton's activity, which is pretty important since phytoplankton's at the base of many aquatic food webs. And besides that, oxygen levels are very much impacted. In Arctic ponds, benthic invertebrates are exposed to sub-freezing temperatures. And in a stream bed, they may become trapped in anchor ice. We all know that freezing isn't good for living animals. When water freezes, it expands, which means when our blood freezes, the water in our blood expands, which causes cells to burst. If this wasn't an issue, then people would probably already be freezing themselves to meet their great-great-great-grandchildren in the future, but we don't see that happening, do we? When water freezes, the water molecules become oriented in a crystal lattice. The process of crystallization is accelerated by nucleating agents that are responsible for holding the water molecules together and then freezing. So, theoretically, if you remove these nucleating agents, then the water wouldn't freeze, right? Well, this is how antifreeze works. Some surface-dwelling fish have evolved their own antifreeze proteins, which allows them to endure extreme cold environments. They release glycoproteins and polypeptides, which lowers the freezing point of their body fluids. This is referred to as supercooling. A fish who is supercooled will enter a state of dormancy. They must stay still so as to not disturb this process and accidentally freeze themselves. This is because freezing can be activated by slight disturbances, despite the creation of these proteins. Some marine fish have a freezing point higher than the freezing point of water, which you can imagine is problematic. I mean, what if the fish froze before the water that it was in froze? Therefore, cold-regioned marine fishes will either migrate up to warm water or to deep cooled water and enter a state of being supercooled. Going into deeper, cooler water prevents exposure to external ice, which might be present at higher depths. Ice can act as a nucleating agent, accidentally triggering freezing in the fish. If a marine fish isn't so much the traveling type, then it stays put in the shallow, ice-laden waters. But in order to do this, they must be freeze-resistant. Poikiotherms are freshwater fish and aquatic invertebrates who function at body temperatures within the same narrow range as the water that they're in. This could be problematic in very cold temperatures, however. Functions become impaired, and the rates of chemical reactions responsible for equilibrium is temperature dependent, which basically means most internal biological processes become very slowed down. Non-hibernating aquatic organisms are greatly limited because for every 10 degrees Celsius temperature decrease, the chemically mediated metabolic rate of a poikiotherm can decrease by a factor of 2 or more. Amazingly though, some poikiotherms are able to adjust their metabolic rate and acclimatize to the cold water, which shifts the organism's temperature tolerance. Metabolic adjustments from changing certain enzyme concentrations allow individuals to become well adjusted to the changing seasons. Other fishes that are constantly in colder waters have the ability to function just as well at colder temperatures because they are acclimatized to the cold water. Seasonal acclimatization can explain why different members of the same population can inhabit different thermal environments over a wide latitudinal range. Just because an animal is able to physically function at a lower temperature doesn't mean that all of the other problems associated with winter just go away. In fact, depleting oxygen levels associated with the winter time can be more of a stressor than the cold temperatures themselves. So much so that in shallow ponds, wintertime fish kills are not uncommon from just the lack of oxygen. For the ones that are able to survive unusually long winters, may switch over to anaerobic respiration, getting their energy from breaking down carbohydrates and turning it into lactic acid. This saves oxygen when oxygen levels are low in the environment. But this can come with its own problems though. Terrestrial amphibians have their own ways of dealing with the cold too. They can bury themselves deep into the soil or hibernate in the mud at the bottom of ponds. This greatly reduces their exposure to freezing temperatures in the first place. However, instead of avoiding freezing, some animals will literally freeze themselves. Like frogs. This frog literally freezes itself. The same pros and cons remain true for these dormant fish as hibernating bears or small mammals that use torpor. Although I'm not sure that bears have to worry as much about becoming dinner.
So overall, I feel like dormancy is a pretty good strategy to be able to survive cold environments. It definitely does come with some setbacks, but for the animals that do have the ability to go dormant for extended periods of time or short periods of time, the benefits have made themselves pretty apparent. Although the ability to hibernate can take generations and generations to evolve, once an animal does have this ability, it then can live in more environments, live even longer than before, and avoids problems like exposure to predation, exposure to harsh environments, and starving to death. Although it is extremely energetically costly to get out of a state of dormancy, the amount of energy that you save while being dormant is extremely higher than if you just decided to try to wait out the winter.